So, yeah, welcome everyone to our fourth seminar, of our ORI anniversary seminar series. So this is the fourth one in a row and the first one in the new year. So I'm really happy and excited to have Michael Beetz here today. Michael was my DPhil supervisor, my PhD supervisor, and has an immense background in robotics and AI. So maybe just to give you a bit of background of Michael's history and in robotics and AI, and then Michael can start with his presentation. And in the end, we will have some time, obviously, to also answer some questions. So Michael is a professor in computer science at the University of Bremen in Germany, where he is heading the Institute for Artificial Intelligence. So he obtained his degree in computer science at the University of Kaiserslautern in Germany, and then did also a master and PhD in Yale University in the US under the supervision of Professor Drew McDermott, where he was working on anticipating and forestalling execution failures in robot plans. Then he joined the University of Bonn, and where he was a professor, and later the Technical University of Munich, where I met Michael and where he was my PhD supervisor. In Munich, he led was the vice coordinator of the German cluster of excellence for cognition of technical systems. And he also led the European project RoboHow, which was about web-enabled and experience-based cognitive robots. This research continued then at the University of Bremen, where he's now, where he is also the coordinator of the Research Center for Everyday Activity Science and Engineering. And I think we will hear more about this in his talk and presentation today. So his main areas of expertise and interests are plan-based robotics, knowledge representation, reasoning for robots, cognition-enabled perception, and integrated learning systems. So I'm really happy to welcome you, Michael. It's really a pleasure to have you here today.
Cool. It's my pleasure, and thanks a lot for having. I first try to share my screen to and I share the sound too. Yeah. I hope you can see my screen now.
Yep, you just need to put it in full screen mode.
So now it should be fine. Yeah, thanks a lot for inviting me, and it's a great honor for me, and I would have loved to come in person, but unfortunately the times are not that we can do that. So I hope I can visit soon. And also the research is kind introduction, and lots of the research that I'm talking about is actually inspired by the thesis research of Lars. Yeah. So yeah, let me just jump into it. So the key problem that I'm interested in is if we give robots underdetermined task requests, something like clean up or set the table or bring me something to drink. So the main problem that we have is we have to equip the robots with robot control programs that can map these underdetermined task requests into specific body motions that achieve the desired effects and avoid unwanted ones. And I think robotics is just finding this mapping. And I think in the age of data-intensive machine learning, right? So I think the obvious solution is that we are looking for this function so that for any object, any task, any environment, any context, and any robot, we basically want to map the task into the behavior of the robot that accomplishes the task. And one approach to go about that is, of course, data-intensive machine learning, where we try to look at that as a function, and we try to get enough examples so that we can approximate the function from this tuple into the right behavior, right? And many people work on that today. And there are spectacular, I think, achievements that have been accomplished with these technologies, and a number of relevant superhuman cognitive mechanisms have been developed. So like solving problems, playing games, very cool realistic simulation of baking, open question answering, and the like. But there are also open challenges, right? So even so that we kind of have these competent cognitive capabilities, I think most of us would agree that we are still far away from achieving something like this capability, right? And this is amazing because I think it's a kind of a skill that is learned very early in life, but and with kind of limited body strength, limited motion coordination, and still so general, so flexible, and powerful, right? And I think kind of one of the things that is obviously missing if we are comparing these approaches, that this boy has some kind of understanding of what he's doing, right? And I think this is what we also need in the systems, right? And this problem, in my opinion, becomes even harder when we look at kind of how that skill of pouring develops over the lifetime of humans, right? So when we basically all start like pouring some water into a glass, we learn lots of variations of pouring. And so we can build, kind of fill beer into a glass, but we also can neutralize acid. We can extinguish fire. And these are all forms of pouring. And most of them we could actually accomplish the first time we are kind of facing that respective task, or we can accomplish the task in novel circumstances. So I think there's kind of the big question is what is missing, and of course everybody has a different opinion about what is missing. So kind of the way I look at it is that one fundamental capability that I think would help realizing computation models that can accomplish underdetermined tasks is if these systems are able to build a model of the action they intend to solve, and they do not only kind of construct the model on demand for the task that they specifically try to tackle, but they also represent that model explicitly so that the model is connected to their experience and to their knowledge, and has a semantics and the purpose of having that representation is that the system can reason about that future action. And reasoning means that it can basically answer open questions about that future actions, like how will I accomplish kind of the effects? What will happen if I move my body differently? Is there a way to move my body to avoid a certain effect? And this capability, I think, is one that to have that is key in robot control systems. So we are trying kind of to build robot control systems that are realized according to these ideas for a long time. And I will just show you kind of a demonstration 1.5 years ago that essentially shows where we are.
Hi, my name is Gaia and I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PR2 is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with the minimal amount of human interference. The first task is to set a table for cereal breakfast for one person. This involves 5 objects: a bowl, a spoon, a cup, some milk, and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash, as it's assumed to be empty then. The perception system that we use is called RoboSherlock. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called GISCARD. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits, and avoiding collisions with the environment. The plan executive that we use is called CRAM. It uses the reactive planning approach, such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick and place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick-and-place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collective experience. For more information, please follow the links in the description below.
Okay, so the main point I want to make when we are watching that video is that we are essentially executing one high-level plan, and that this high-level plan essentially specifies that objects should be put where they belong. And this high-level plan is implemented by a loop, which basically says, for every object that it's not at the desired place, fetch it and put it where it belongs, right? And everything else that you see in terms of behavior of the robot is actually derived from the internal knowledge of the robot and its reasoning capabilities. So the basic mechanism that we have, or the way we put that, is that we are specifying generalized action plans for categories of tasks like fetch and place, pouring, cutting, and we have plans that specify the motions that have to be executed in order to accomplish these generalized plans. And the mechanism that basically specializes a generalized action plan into a motion plan is contextualization. So we take essentially the task and the specifics of the context and the background knowledge in order to specialize the generalized plan into a motion plan. And I will explain a little bit how the plans are written and what that reasoning is doing. So the generalized action plan for fetch and place looks essentially like that. You fetch an object and put it at a particular destination, and you do that by executing the following body. So at a location where the object you want to fetch and place is visible and reachable, you perform the action of fetching the object. And then at a location where the destination is visible and reachable, you are performing the action of placing the object at the destination, right? So that's kind of all. So the game we are playing is we are specifying the plan very abstractly, very vaguely, and allow hand waving, which makes the plan very general. So the advantage of having these very general plans are that we can combine them with knowledge. So, and in particular, general and modular knowledge pieces. So we can basically have knowledge pieces like cups used for table settings have to be clean and unused. Cups in cupboards are clean. Cups have to be gassed from the outside. We can have very general knowledge chunks. So something like you should parameterize the motions to avoid unwanted side effects. And spilling is an unwanted side effect of pouring. So this is kind of a piece of knowledge that is kind of very general, but also very expensive to compute because it kind of requires you to mentally simulate what's happening when you execute it. And you can have also knowledge chunks that you can learn from experience, something like the pose to pick up a heavy pot that you can, for instance, learn through data-intensive machine learning. So the second kind of representation of the action is a motion plan. So essentially, we take models from cognitive psychology, in our case, the Flanagan model of actions, which kind of decomposes the motions of fetch and place into motion phases like reaching, lifting, transporting, and releasing. And reaching is essentially has a goal of the hand having contact with the object. Lifting has a goal of lifting off the object from the supporting surface. And we are specializing these phases by basically refining it into a more fine-grained model that allows us to synthesize these actions. And you have seen in the video that the way we are parameterizing the plans at that level is sufficient to perform tasks like table setting in the way we've shown that. So there's another kind of mechanism that we need at the motion level, and these are task-critical motion patterns. So task-critical motion patterns are constraints on motions that need to be satisfied for the motions to have the desired effects and avoid unwanted side effects. So for instance, if we have the task request, pour the water out of the pot, task-critical motion patterns are grasping the pot by the handle, holding the pot horizontally, tilting the pot around the axis between the handles, and so on. So kind of you want to define these constraints at a semantic level, and you can basically implement them in your motion control system using constraint and optimization-based control methods. So if you have that vocabulary of mechanisms, so how is then the process of contextualization working? So what the robot gets is an underdetermined task request. So something like you have to perform an action of the type fetch and place with an object of the type cup, where the destination is an object type kitchen table. With this task request, it finds the right generalized action plan and instantiates it with the formal parameters. And here, so for instance, we get an object type cup to be fetched. We also extend the plan body with the parameters of the motion plan, right? The arm that has to be used to pick up the object, the grasp type, the lift pose, and so on. And then the central inference task, at least in a nutshell, is for the robot control system to identify the parameters at the motion plan level such that if the motion plan is instantiated in this way, the action will succeed to accomplish its desired effects and avoids unwanted side effects. So that's kind of the central inference task that a robot control system has to do all the way and all the time. So we are building a cognitive architecture for robot control systems that implements this idea of controlling autonomous robots, right? So you see here the generalized plan executive. But in order to realize that, you need a knowledge representation and reasoning system that can answer all the questions that the plan executive is asking in order to execute an underdetermined plan. Right? And I will basically talk in the rest of the plan mainly about how that knowledge representation and reasoning system can be designed to actually satisfy these requirements. So just to go back to the video we have seen. So the control program you have seen is mostly one generalized action plan, that the one that I've shown you, with an hand-coded knowledge base. And essentially it's effective to solve a task like table setting, but it has to do a lot of backtracking. So the performance of this basic program can be substantially improved if we add prospection mechanism of the robot. So if the robot at the time of picking up an object already reasons about how it will later put down the object at the destination, then we will be substantially better than without having these prospection mechanism. Another way of improving this basic plan variant is that we take the basic plan variant, we record kind of for every episode an episodic memory, and we learn from experience what are the parameters for the motion plans that are expected to perform well for the task. And again, you get, of course, a system that outperforms the basic plan. You cannot do the same kind of thing not by collecting the experience with a robot, by the robot observing humans doing that. The advantage of doing that is that the learning process is much more efficient because humans have common sense, so they will kind of have much fewer failures in accomplishing tasks. And so you get more valuable training examples for your learning task. And you have other ways of learning that. So let us now think about what are the basic mechanism and the basic functionality that the knowledge representation and reasoning system has to have in order to have this functionality. And as I said, so I think the basic capability we want the knowledge representation and reasoning system to have is that this system can compose the actions that the robot intends to explain, to execute before it's executing them. And it does so in order to imagine how the execution will go. It will model that execution and represent it, and then it can explain predicted effects. It can basically use that for planning the best parameters. And it will do that on the underdetermined action description that the robot gets. And the way it's doing these reasoning tasks is that it uses an inner model of the world, but that inner world model is not only a simulation of the environment, but it's also machine understandable. And I will explain what that means. So the inner world representation is essentially a game engine model of the world. So you have the robot and you have the environment, and both interact by the robot perceiving images from the environment and executing a body motion, which then has physical effects in the environment. And we are trying to kind of model all these aspects as realistically, as detailed as possible. And if we are running these internal representations of the outer world, we basically record every manipulation episode into an episodic memory, which is a complete brain dump of what the robot did when it was accomplishing the manipulation task, together with all its perception and all the motions that it executes. But we also use a second representation, which is a symbolic representation of the same action and the same manipulation episode. You can imagine that this symbolic representation contains hundreds of thousands of facts of all little aspects of the environment, right? And the reason that you want to have this symbolic representation of that environment is that you want to ask open questions about what is happening, why are things happening, what do you expect to happen, how can I avoid certain effects. And symbolic knowledge representation and reasoning gives you that question answering capability. So the question is, of course, how can we have such very comprehensive symbolic knowledge bases? And here, kind of the big insight is that we can essentially implement the inner world model, so the simulation infrastructure and the symbolic knowledge base in the same way. And we are doing that by essentially using the scene graph data structure of the game engine environments and casting them as virtual knowledge bases. So whenever the robot is performing a reasoning task and asking about facts, the virtual knowledge base is retrieving the information about these queries from the scene graph and casting them as a symbolic fact to the reasoning engine. So essentially, it's kind of a lazy symbolic knowledge base that only translates the part of your model that you need for reasoning on demand into a symbolic representation. So these are the main points, right? So you want to have symbolic reasoning in your robot control system because symbolic representations let you represent your knowledge in modular, composable, generalized knowledge chunks. You can also do semantic reasoning problems through the mechanistic manipulation of symbol structures, right? And that's kind of very cool if you want to solve manipulation tasks that you have never seen before. Kind of the big problem with symbolic representations is that typically symbolic representations are too abstract to actually infer things that are relevant for robot control. So we overcome that problem because our symbolic facts are linked to the scene graph, and the scene graph is a representation that kind of matches in detail the world as it is, right? So there are two big advantages, right? So for one thing, we have a grounding for every symbol in our symbolic knowledge base that is an entity in the world that you are modeling. So you have essentially a strong grounding of your symbolic representations in the scene graphs. The next thing is, because it's a scene graph and because simulation engines work with scene graphs, we can use the scene graph to do mental simulations and imagistic reasoning. So that enables the robot to actually reason with its eyes and hands. And also, so it has very detailed models of the environment, and that it needs, because if we are controlling motions, we essentially have to give positions and poses to the robot, which are in essence concrete pieces of information. So the way we are basically casting this scene graph is that we have predicates that compute their truth value based on procedural attachments that work on the scene graph. So we can have, for instance, a predicate expected image that runs the rendering engine of the simulation engine with the pose of the camera and the camera parameters and returns an image that the robot sees yet. So then we can kind of assign each entity in an image a different color, and we can ask for the image that is rendered this way, and then we get a perfectly segmented image this way. Or we can ask the question of kind of the XY positions in the image of a certain object, and we get a perfectly cut out region that depicts a particular object in a scene. So by casting virtual reality representations as symbolic knowledge bases, we get a very powerful knowledge representation that lets us ask symbolic queries with kind of predicates like holds, occurs, and entities. So for instance, we are looking for an entity act that is an action of the type grasping for an object of the type spoon that occurs in a certain interval, and where the spoon is at the beginning of the action interval on the table, and the table is indeed of the glass table, and we want to show the spoon, or we want to basically, we are asking for an action of the type putting down, which is a sub-action of fetch and place, and we are looking at the trajectory of the hand in that particular time interval. So kind of the big thing is that your symbolic knowledge base is then a semantic index mechanism on your sub-symbolic experience stream, right? And if we are using this kind of knowledge representation for robots using an inner world, so for one thing, we get much better models of the world, but also some computation tasks become a lot easier. And that's because the representation is much closer to the representation that the robot gets in the perception action loop than the abstract representations. So here you see on the left hand, the belief state of the robot, and on the right hand, it was the real world. So the perception system is then working that whenever it perceives parts of the world, it tries to reconstruct what it sees in its inner world model. And if you're doing that based on known objects in the environment, it's just kind of identifying the right object, putting it in the right place. But the gain is that you have a very detailed representation of the world. You have the complete context of your task, and you can make many inferences also about things you don't see, because you have the simulation also running in your internal world model. So this is the way So whenever the robot acts, it's actually using its inner world model to make predictions about the world. And of course, many of these predictions will be wrong. So the robot control programs and the plans have a heavy load of failure detection and failure recovery mechanisms. So in our plans, about 90% of the code, I guess, is failure detection, analysis, and recovery. But then still kind of the information that so detailed models of the world give you in order to select the right action is so valuable that it's actually worth doing all these failure detection and recovery kind of steps and work. Sorry. So the second step is we are using also, the robot is using the inner world model in order to simulate what it's doing. So you see here in the simulation that we are running essentially exactly the same programs that you have seen in the milestone demo on the real robot, right? You have the same behavior of the robot. And this is essentially what the robot always is running internally before it executes actions and reasons about them. You see kind of the same kind of thing on the real robot. Of course, kind of the behavior is highly non-deterministic, so comparing the both behaviors one-to-one wouldn't tell you a lot, but you see qualitatively that it's the same behavior and the same kind of failures and repositioning in order to see and reach the object in a better way is happening in simulation as it does in the real. Okay, so the point is, whenever we basically have actions running in inner world model, the system automatically interprets these actions. So we can see that in the following video. So so here we have an inner world model running, but now we run it essentially with a human instead of a robot acting in the world. So that's kind of a setup we use, for example, for imitation learning. And so you see that the system is recording the activity in the real world, in the simulated world. And here is how you see how the system is interpreting the activity. So in the same way as we have seen in the motion plan, kind of the meaningful events that have to be detected in the world are the force dynamic events. So contact of the hand with an object, something like lifting objects off supporting surface, opening containers so that they become open and things like that. These are the meaningful events that have to be detected. If you are detecting these events, then you can have a parser that basically takes the event stream and translates it into a hierarchical action model. And that can be done automatically without human kind of annotation or anything else. So that's kind of event detection. And now you see event recognition. So whenever kind of an action is passed and detected, we are able to query our internal world model about the action, and we get visualization of whatever we are asking in the query. So here, the trajectory of the hand when the action getting out the milk box of the fridge is executed. So here you see how we are pushing that these simulations get more realistic in terms of physics simulation, so that we can cover larger varieties of manipulation capabilities. And here you actually see that these inner world models, these game engine environments, they can be completely constructed out of the symbolic knowledge base. We are basically loading a symbolic knowledge base, and in that symbolic knowledge base, we are looking for all objects of certain types, building, furniture, items, and then we are creating the items at the respective positions in the game environment, right? And you see how the simulation environment is constructed out of the symbolic knowledge base. And now you can basically take all your symbolic query language in order to query every aspect of the environment, like kind of the handles of the container objects, the electrical devices, and other objects, right? And we can replay the inner world out of different perspectives. We can use different environments. And here is the way how we are building models of particular actions. You see, again, it's the same plan that we had in the robot control system with the same kind of phases. And it's automatically segmented here. And we are getting all the informations we need in order to interpret the actions, right? So, let's see. And we are getting, by people accomplishing table setting tasks and cleaning up, essentially large amounts of episodic memories we can use for learning. So here you have information about how entities are placed in the dishwasher for the robot to learn to load the dishwasher, right? And you get the trajectories. You get the trajectories for different objects to the different things. Okay, so I think that was essentially what I wanted to talk about. So I think my conclusion is that I would expect that the next generation of robot control systems are using, again, symbolic knowledge bases, but knowledge bases, symbolic knowledge base that are much, much more powerful. So you have seen in the area of deep learning, so how essentially big data and kind of computational power has been exploited in order to kind of get a huge step change in performance of learning systems. These kinds of technologies haven't been exploited in the same way for symbolic reasoning yet, right? So, and I think it's kind of, it's interesting to see if we are applying these technologies, in particular, virtual reality technologies, big machine learning technologies, and apply it in these kinds of contexts. I think I would expect the next generation of knowledge representation and reasoning system to be much, much stronger. I also think that if we really want to understand intelligent systems, I think one of the key tasks is how intelligent systems generate physical actions in the world, right? So that's, if you're looking at the evolution of intelligence, that's one of the key driving forces that that has promoted the development of cognitive capabilities. And I think if we want to understand better possible computation models of intelligent systems. I think physical actions of robots is one of the things that we kind of have to do research on with the highest priority. I also think that the disruptive advance in game engine technology, machine learning, hybrid knowledge representation, and reasoning data science make that kind of research agenda feasible. Thank you for your attention, and I'm happy to answer questions.
That's great, Michael. Thank you so much for your talk. That was really, really impressive and interesting to see all the kind of use of the game engine and connection with the knowledge base and representation. So yeah, everyone, please feel free to put questions in the chat, or maybe raise your hand if you want to ask it directly. So yeah, please, if you have any questions, please, we can collect them in the chat now, or if you want to raise your hand, so then we can also discuss them. So while you're thinking about your questions, so let me start with one of the with the first one. So in particular, if you think about kind of open-ended environments, it is obviously challenging to deal with new objects or kind of potential new actions that you're learning, or maybe new contexts that you haven't seen before. So I was wondering how you think this builds in with or works with your knowledge representation and reasoning. So how?
Oh, sorry, I think I didn't have audio at the moment. Yeah.
Oh, okay.
Sorry, just came back here.
Okay, great. So I was just asking quickly about the kind of challenges with respect to open-ended environments and how you would think this works with the kind of knowledge representation you are using, because you would need to add new objects, new actions, or new contexts somehow.
So yeah, so I think it would work just fine. I think in particular, you have that scene graph representation. So it's like going from kind of navigation in a known environment to SLAM, right? So you kind of want to build up your models and your acting at the same time, right? Mm-hmm. But I think it would actually be a very cool way of realizing that, right? Because in a way you can already build entities in your scene graph, give them symbolic names, and then you can actually refine the scene graph as you learn more about the object. You can also collect knowledge. Yeah, so yeah, as I said, I think it's just like going from navigation in a known environment to SLAM. But I think in terms of the representation infrastructure, you have actually great support for doing that kind of thing, right? And yeah. Mm-hmm. And I think there's also a whole lot of work in inverse rendering, right? So where actually people in deep learning look at how to actually guess what the objects are from renderings of the world. I would also see these kinds of technologies to be kind of tools that would actually make that more feasible.
Mm-hmm. Yeah, thank you, Michael. So there's a question from Ingmar. Ingmar, do you want to unmute yourself? And
sure, Michael. Firstly, let me say thank you for the talk. I always am totally blown away by the kind of stuff that you get your robots to do. I think that's always super impressive, and also the sort of zeal with which you follow this sort of vision over the past years in putting a lot of these systems together. I think all of that is super impressive. One thing that I'm super excited about is the question of learning these world models, right? Particularly the object-centric ones. So the idea there clearly is to somehow get the connection done between the observations and sort of the symbol grounding, and thereby discovering the symbols and discovering what kind of actions you can perform on what symbols and so on. And I'm wondering how you look at that body of literature and how you see these things eventually come together, or not, as the case may be.
Yeah, so I think, again, I think the way we are looking at it, it's kind of a little bit different perspective, right? So because if we are looking at the representational infrastructure, it's considering the inner world model, right? So if people in other research areas, be it knowledge representation or also mapping, the reference structure is the outside world, right? So, but we are actually grounding everything in the inner world model, right? And we have essentially monitoring processes in the control system that always correct the inner world model to make it fit with your experience, with your actions. So whenever you fail, you're correcting kind of your inner world model. And yeah, so kind of you don't have the correctness of or kind of accuracy of your models in with respect to the real world, but kind of you have perfect measures of performance with respect to your own actions, right? And I think for that, the models are just great. And I think also for me, kind of grounding representations in inner models makes much more sense than grounding it into the outside world, right? If you do it with inner world models and you have distributions of inner world models, you can talk about things like the robot is unsure about which state it is and things like that. You couldn't do the same kind of thing in the same way about outside models, right?
Mm-hmm. Yeah.
So I think it would be at least kind of another way of going about that. And I think I would hope that kind of there are also things that become easier this way. Yeah.
Great, thanks.
Great, thank you, Michael. So there was another question on the episodic memories, and so whether it's more use the term in a psychological sense, so that the robot can recall a specific past experience, or more like a consolidation of experience regarding specific scenarios that the robot can draw on for planning and prediction.
So the way we are using it's not like people in cognitive psychology. For us, it's actually a recording of a manipulation episode, which is essentially kind of semantically segmented and annotated with the robot's internal model. So it's essentially building kind of experience data structure of all the robot poses, all the images, plus the story that the robot tells itself about what it's doing in great detail when it executes the plan, right? But this way, it can basically say, after it has executed an episodic memory, it can say something, give me the sub-episode where I have picked up objects with two hands, right? And it could automatically link them in the sub-symbolic experiences. And I think that's kind of very powerful. So we are looking at episodic memories at this time much more as a data structure or kind of a knowledge structure, but it's heavily inspired by how people kind of in cognitive psychology look at them.
Yeah, thanks. So then there is another question about plan optimization. So if I understand this correctly, maybe you can explain a little bit how you, for example, do this kind of planning in your inner world, and how you then optimize your plans by maybe skipping some of the steps and seeing whether it's still okay, whether you're still succeeding or whether it fails. Are you pursuing something like this?
So we are doing much less generative planning. So planning basically by chaining action step by step. So kind of what we are doing is essentially running the simulations see when we execute the actions in the intended way, whether that will kind of lead to failures. And if it leads to failures, whether we can find patches or kind of other parameters that avoid these failures. So that's kind of one way of doing that, right? Another way is that we are looking at episodic memories that we get from humans performing these tasks. And we are looking for surprising things, right? So the surprising thing would be if the robot executes kind of closing the drawer, it would have to use the hand and push the drawer in, right? But if a human does it, it could be that the human actually closes the drawer with the foot, right? And of course, there is a big advantage because you can then close the door kind of when you have objects in both hands, right? So, so the robot would actually detect that this is kind of a goal which was achieved in a surprising way. And it would actually kind of try to apply that kind of pattern in other episodes to make the episodes more efficient. And that's another way. Again, I think the main driving thing is seeing ways that are surprising and efficient. So, for instance, the robot would carry objects for setting the table one by one, but it would see that the human is, for instance, using a tray. And then the number of times it goes back and forth between the cupboard and the table is much lower, right? So that, again, that's kind of surprising. But then it has to learn that actually by putting objects on a tray, carrying the tray, and kind of unloading that this is another structure of a plan which might be more efficient in some ways, right?
Mm-hmm. Maybe just as a follow-up question. So these surprises, would you think that these are detected on the symbolic level, or where do you think?
Yeah, I think it's kind of the way we are looking at it is it's actually at the goal levels, right? So you're noticing that certain goals that you have in the plan are kind of suddenly achieved without you doing something for it, right? Essentially, and I think that's kind of the driving force for basically looking at that structure.
Mm-hmm. Okay. Yeah, so I think unfortunately that's all we have time for today. Thank you again, Michael, for this really nice presentation, for taking the time. And also everyone for joining and for the really interesting questions. So yeah, a big hand for Michael. Unfortunately, only virtual here.
Yes, thanks a lot for attending, and I'm looking forward to visiting. Yeah,
you're
bye
always
bye.
welcome. Okay, great, everyone. Thanks for joining, and yeah, see you all soon.